Is that your laptop or there's some sound, right?
No, not mine.
Oh. Okay, so let's get started. Okay, so let's get started, guys. You can do that probably during the break, or you want to exit, that's fine too. Okay. So let's get started. So we are on lecture 4. This is right before assignment submission next week. So assignment 2 is about CNNs, which we have covered in the past couple of lectures. And it's also some initial foray into recommendation systems, but really it requires just the understanding of embeddings, but we've already seen embeddings in when we talked about images. So embeddings are just vector representations of things. They're most popularly used for text as well as images. So text embeddings are just vector representations for words, and we have seen vector representations for images already, right? So that is the information needed to kind of work on the second part of assignment 2, second question. But I'll briefly go over them actually right after this. But I wanted to tell you that we are here, and today what we'll do is continue where we left off last time, which is talk about just wrap up transfer learning again, kind of recap actually, and then look at the remaining of that lecture slide deck, which included things like dropout, batch normalization, and data augmentation. So some concepts from last slide deck, we'll revisit that. And then we'll look at today's some part of, so we are kind of a little bit lagging. So today we'll look at intro to NLP essentially. which really is not an intro to NLP, but intro to some models, non-deep learning models for NLP. Okay, so obviously NLP is a full-fledged course, so we're not going to cover everything that's there in that course, but we'll look at some models that you might have seen before for working with text. Okay, so that's the agenda to kind of recap transfer. I'm not going to recap the entire thing, but recap the LoRa aspect of it, which we saw very quickly the code base last time, but I want to kind of revisit that and then look at some practical, not models, but practical considerations, which include the engineering things that I talked about, and then intro to NLP. So those would be the three buckets. So recap of transfer, dropout and batch normalization and whatnot. So engineering ideas, and then the last part would be intro to NLP. But before I get to that and lecture goals, I wanted to quickly mention assignment 2. Assignment 2 is a fine-tuning assignment. So it's really about transfer, which is what we covered last time. And today we'll talk about LoRa, but LoRa is not part of the assignment. So so in that way, it's not, I mean, although we'll cover it. Assignment 2, first question, is just a adaptation of an existing Python notebook. In fact, it's from pytorch.org's tutorial. In that tutorial, they're trying to use the 1000 class classification model. ResNet and VGG and AlexNet, they're all 1000 class classification models trained on ImageNet. You want to kind of use them and fine tune them to solve a 10 class classification problem. Okay, so you're going to use a pre-trained model called ResNet 18. And there are several versions of ResNet. ResNet stands for residual networks, which is a slight variation of a CNN. And you'll see what ResNet is later. Okay, so we'll not go into details, but you'll see what the residual network connections mean. If not explicitly in the ResNet case, you'll see residual connections in some other models. So you'll kind of see what residual connections are. So that's what you're doing. So basically, a 1000 class classification problem, you want to adapt it to a 10 class classification problem. The 10 class classification problem, it's a data set called CIFAR10. Okay, so that's the data set. You can get the data set. And the big challenges with this question is just arranging a data set. So arranging the data set either to in the same format as what is expected in the tutorial. So there's there is a code base, not tutorial, sorry. There's a code base which is part of a tutorial from PyTorch tutorials website. That code base is in the repository examples, right? Sorry, this classifier example, and if you open it, you'll see that there's a link to a more live version of the code also. So that code base is doing a 2-class classification. It's basically classifying ants against bees. Okay, so these are just 2 insects, and there's a 2-class classification going on. Instead, we want a 10-class classification. Okay, that's the only difference. Obviously, the difference in data set. So you should be able to understand. So challenges in the assignment is just to understand like what's going on in this new unstructured data set. It's not very similar to scikit-learn flow. It is similar, obviously, at the very abstract level. It is the same thing. I mean, data prep, fit, fit, transform, whatever, and then eval. But you'll see the nitty-gritties of using, let's say, PyTorch objects in between to kind of define what is the data set, what is a data loader, and so on. So you will kind of appreciate why those things are needed while you go through the workbook. Okay, I'll also mention today, some additional details about these objects when we recap the LoRa tuning example. Yeah.
In terms of this first part, you said we're not going to use LoRa in terms of the fine tuning, but
in this one, yeah.
Do the other thing where you kind of go back a couple layers.
Yes. Okay. Yes. So we'll do both. We'll do fixed feature extraction, as well as the fine tuning. Fine tuning includes fixed feature extraction when learning rates are 0. Yeah. We're doing both. The 2 types. Yeah. We're just not doing the third one, which is LoRa. Yeah. The second one, this one is about embeddings, but these are not even not text embeddings, not image embeddings. We want to embed movies. Okay. You can say movies are abstract objects. They're not exactly like words, but if you want to think of them as words, you can. But basically, what we want is for every concept or entity or object called a movie, we want a embedding of it, as in a vector representation of it, as in a bunch of numbers corresponding to it. And a priori, we don't know those numbers. And so that's what we want to learn. Okay. So, if you can get embeddings of movies, let's say, somehow you were able to figure out and learn these numbers, and we'll get to that learning part in a second. But if you're able to embed them, so all the movies are in, let's say, 10-dimensional vector space, then you can actually do just nearest neighbors to get a sense of, oh, if this movie, then what are the nearest neighbors to those movies and so on. So you could potentially recommend if you could embed them into vector spaces, right? So that's at least the basic idea. Obviously, you can do a lot more here. So all these questions, maybe not the first question, but the second question is a little bit open-ended. You get to choose a few things here, how to recommend and so on. But then let's come back to the core question, which is how do you get these vector representations of movies? So here, basically what you have is for every movie, you have a user who's rated that movie. And so this is a very standard data set called the movie lens data set. I don't know how many of you have heard of movie lens data set. Okay, just one. Nobody else. Okay, so this is a standard data set of movie, some user, and some rating that they gave. So what you want to get is this is just data prep step, okay, which is called this movie cross movie matrix X. Okay, it's just a matrix. It's just a data prep. It's nothing to do with deep learning. What you need to do is, for a pair of movies, figure out how many common users watched both those movies and liked it. Okay, that's just a data prep. You just can, since I told you the data set is basically for every movie, there's a user and some rating that they provided. So you can pick two movies. Maybe those two movies were watched by, in terms of common set of people who watched it, there are only 10 people. And maybe out of those 10 people, 5 of them rated as like amazing, 5-star, and then remaining people just rated it as like 1-star or something. So that's the type of data you have. And so from that, you can extract a number for the Xij entry of this matrix. Okay, this is just a data prep step. And once you get that data, that for a pair of movies, how many people liked it commonly, like some sort of account or some normalized count, then you can use that as data for your loss function. Okay, so the loss function is just this, some sort of squared loss, where I told you the data part. What is the model prediction part? If we had vectors for movies, one vector per movie, then my prediction for how many people, let's say count of how many people who would like it, is going to be just the inner product of those two vectors. That's why I wrote, like, the model is very simple. There's no extra, dangling ax plus b or something like that. It's just, if I had these embeddings, then the inner product of those two, which will result in a number, is my prediction of how many common number of users would like those two movies. Okay.
It's the same as the Netflix data set.
It's not the Netflix data set. It's a movie lens data set. Is a different
Format of Netflix.
I don't even know what the Netflix data set format is.
We use for the recommendations.
Yeah. But I don't think Netflix itself gave a data set.
I don't know, it's in text format.
Yeah, it'll be very similar. Actually, this data set. Actually, you can. I don't want to download it, but it is it's a CSV file basically. You can see the. I don't know. Yeah, so user ID, movie ID. You can tag. Actually, we don't need tag. We want this one. Ratings. Yeah.
First, we find out the number of common users that like those particular two movies. Then can you explain the?
No, I mean that's already mentioned here. I'm just telling you.
Okay.
I mean that's how you would process it, but that's a data set. Here we are saying Xij is the number of users that like both movies. You need to go from that data set to that matrix, right? You need to figure out how can that data set answer this question? Can I get Xij? You figure it out. I just told you the answer also a little bit, but you can code it. This is the data pre-processing part. Once you have the data, the modeling part is just that I don't know the vectors, but if I knew the vectors, the inner product is what is predicting this number. And you've just computed the numbers from the data prep, so that's just data. You're not changing it. So now you need to figure out what are the parameters of this vector such that it predicts these numbers well. Okay. So hopefully that's clear. Yeah, and you'll see. I mean, there's some creativity here. I'm not giving you one more part of it, which is going to be some uncertain thing to do, but you'll see if you try it. Okay. So I mean, ideally, I would have liked to cover text embeddings before this question, but text embeddings are not precursor. I mean, not a necessary thing to know before this. It's just that you just need to get some embeddings for, just like you got embeddings for images, you need some embeddings for movies, and that's what you're learning here. You're just learning the entries of these V vectors, one per movie, by just doing backprop. So the parameters of vectors are the parameters of this model. You just learn the vectors, so better predict the X values that you pre-processed and figured it out. Once you have vectors, then you can just figure out how to do nearest neighbors or some variation to make recommendations. So it's a little bit open-ended, but that's also how real world is. Generally, there's some business value to be created, and the technical of the textbook solutions are not going to match that. So there's always going to be some assumptions, some adaptation that's needed. Okay. Okay. With that, let's actually now talk about today's goals. Let me just open this for a second, but I will not get there. Okay, so I'm gonna continue where we left off, which is I'll start. I won't start with this, but I'm just listing the goals. But I'll start with a little bit of recap of not exactly transfer learning, but LoRa, because that's a little bit new. It's actually a recent 2-year-old technique. Okay, 2020 or 3 years old now, 2021. So we'll recap LoRa, but in general, transfer learning. But today's goal is to look at a couple of tricks that we'll introduce. I'm just calling it engineering tricks. Hopefully that doesn't seem like it's not worth knowing, but it is actually a couple of good ideas. Okay, so beyond just defining blocks and arranging them, there are a couple of nice ideas that have been used. So we want to kind of learn them, and they can be applied to any model. It doesn't have to be CNNs. It can be also other things. So dropout and batch normalization are the 2 ideas, and one more thing called data augmentation. Those are the 3 things that we will see. Okay, that's the goal for today, just to learn them and appreciate what they are. And then we will get started with lecture 4. In particular, we'll see, not so much about how natural language elements of words are processed in an analytics workflow. Today, what you can do with NLP is very different from what we'll do in the class, in the sense of we are going to only look at basics. Okay, obviously we will look at, maybe not in this lecture, lecture 6 actually. It looks at advanced NLP, in fact, a model architecture known as transformers, which is actually the backbone behind many of these architectures or many of the products that you have seen, like Bard and Claude and what's the other one? ChatGPT and all these ones. They're all based on the same architecture, except they have a lot more behind the scenes proprietary technology, which we don't know, but also a lot of training data and all that. Okay. But for today, we'll look at just the second bullet point. First is just a more general understanding. Second bullet point, which is some other models, non-deep learning models, naive-Bayes, which if some of you have done machine learning, you would have done a potentially naive-Bayes model, like machine learning or data mining. And the second one is called latent Dirichlet allocation. We'll understand what is latent, what is Dirichlet, what allocation means when we talk about it. Okay, those are a couple of models that we'll see today. So that's the agenda for today. So that will, I guess, come towards the really second half. Any questions about what we want to do today? I know that we are kind of chopping a second half of one slide and first half, second, another set of slide, but we want to go slow and absorb the material in a reasonable pace rather than hurrying through things. Yeah. Okay. So let's get started. And the starting point is actually the same code base that we saw last time. I wanted to, I don't want to kind of, okay. So just to give a sense of what we are talking about, right? So last time we kind of covered transfer learning, okay? Kind of in the sense that we covered fine-tuning and fixed feature extraction, 2 ways to repurpose pre-trained model, like a model trained on ImageNet for any potential like a domain-specific task. Of course, you can say ImageNet trained model might not be applicable for medical images. Maybe that's true. But ImageNet model may be useful for like doubling down on maybe, ants versus bees, or like in our case, like airplanes versus houses, which is the situation in CIFAR 10. So maybe they are useful. Okay. The pre-trained models, the weights, which learn some of these patterns that we talked about, like lower level patterns to high level patterns, maybe they're useful. And that's what it's relying on. Okay. And the third type of it is also transfer learning, but the third type of idea is about transferring through tuning, but not tuning the original set of weights at all. Like not changing, not touching them while tuning, but instantiating a couple of other parameters. In particular, for example, if you have a matrix in the original model, you will instantiate two matrices which are skinny. One you can think of it as like a one skinny matrix and one fat matrix, and then if you multiply them, they kind of have the same dimension as the matrix in the original network. And instead of adapting or instead of tuning the original network and losing the original weights, you keep the original weights intact, but change these new parameters that you've instantiated so that now you can do well on your downstream or whatever your task is. Okay, so it's exactly the same as fine tuning, except that you're maintaining the original weights frozen and kept as is. Okay, I mean, in that way it's similar to fixed feature extraction, but fixed feature extraction is only creating some new parameters downstream, whereas here we are creating new parameters in parallel, and that's the key idea. Okay. Yeah. So what I want to do is go over this code, and it's mostly because even last time when we went through this code, it seemed like, oh, there's so many function calls, unknown things going on. But that's because you will see that let's say we settle on PyTorch as our predominant package to do deep neural network training and inference. So it's good to kind of get used to some of these primitives. Okay, it's first time you see it, they seem new. But just like scikit-learn, the second time you see it, the third time you see it, it's kind of the same ideas. Okay, so that's why I wanted to kind of check this code again. Actually, let's I don't know, is it connected? Let's try. Okay, so a bunch of imports. One, I guess, tangential import TQDM is just so, it's a nice package that you can use whenever you have for loops. You can add a TQDM function call onto your thing that you're iterating over, like a list or something like that. And and what it does is give you a nice progress bar. Okay, so it's a nice handy additional package to import if you want to have a progress bar. Okay, so the second thing is something called PDB, and that's one of the secondary reasons why I wanted to look at this code is I know I mentioned PDB a couple of times. How many of you are very familiar with PDB?
Not very familiar.
But you have used it before. Okay. Yeah, so this is something that will come very handy, especially if you're relying on Collab. Okay, so in addition to doing in addition to some of the features that Collab itself has, you can actually look at variables and stuff like that. I don't want to, yeah. So you can use UI to kind of look at what variable values are, what are the dimensions, and so on. And that's true even with Collab or as well as Jupyter. Like if you run Jupyter through Anaconda or something. But it's always good to know a debugging tool. So debugging one step more, I guess. One first way of debugging is just print-based debugging, right? So if there's an error happening, you just wait. Oh, which line error is happening, you print things right before it, for example. That could be an intuitive way to debug. But another way to do, just one slightly different way to do it is to insert essentially what is a breakpoint. Okay, you stop the execution of the program at that location, and then at that location you can kind of probe around and see, oh, what are the variables? Is the input wrong? Is the function wrong? Like, is it doing divide by 0 or something? Like, these are the investigations you can do. And in particular for Torch and in most of your deep learning exercises, one of the big challenges is to ensure that the dimensions are correct and you are expanding the dimension or reducing the dimension, or you're manipulating for example, to concatenate vectors or tensors, you need to have the right dimensions. Okay, that could be a big source of error. And just saying that in addition to print-based debugging, you could use something like VTB to debug. Okay. Okay, so I think I believe I ran the whole thing. It's running actually. Okay, let it run. So firstly, to make torch deterministic, and this is a very, very important thing. I don't know if anything which involves randomization. So for example, in random forests, there could be randomization in the choice of variables, columns, and rows that are being picked. I don't know what's the source of randomization, depends on the package. But if you want to have repeatable results, so that the next time you train the random forest model, you get the same answer, you want to have what is called a seed, okay, random seed that needs to be set. Okay. Same thing with numpy.random, right? If you do numpy.random.random 2 times, and you'll get 2 different answers. And if you actually, maybe it's the same time, but you open the notebook second, maybe 10 days later, run it for the first time, you get different numbers. That's because your seed is not the same, and so you won't get repeatable results. Okay, so you want to kind of eliminate that source of uncertainty. But setting a seed doesn't mean you're kind of killing the randomization. It's just that it's the computer is generating a pseudo-random number sequence, and so you're just kind of setting the starting point of that pseudo-random number sequence, so that you start always from the same part of that sequence. Okay, so this is a very important trick. The next couple of things are basically things that you will see in assignment 2, question 1, which is the notion of transforms. Okay, one of the transforms you'll see is something called transforms or normalize. It's basically the image statistics of ImageNet data. So imagine a situation where the ImageNet data, all the colors are too bright, and in your application, all the colors are too low, or it's dark colored images. Right? There's a kind of fundamental mismatch in the image statistics, as in each channel of the color images in ImageNet have the mean values of the intensity, for example, could be high, and then the mean values of intensity in your data set is low. So there should be some way to kind of that itself could be leading to bad transfer. Okay, bad way of transferring, reusing pre-trained model weights in your application. So one of the tricks is to normalize, as in reset, to kind of push your data set to be having the same data set statistics, by which I just mean the mean red color, the mean green color, the mean blue color, or the standard deviation of those colors to be the same as the big model that was trained, like the ImageNet model. Okay, so that's done using this transform called normalize. The other, I mean, this is just 2 tensor, is just changing the, I guess, from NumPy to a tensor. You will see some transforms today in the data augmentation part, so I will not talk about it. The second object, so transforms is one thing that you should focus on. So this is something that will be very standard in any image learning, any image-based training prediction problem. Okay, whether it's object detection or classification or whatever it is. The second object, which is not specific to images at all, I mean, it's just a style of defining things, is the notion of data sets and data loaders. Okay, so I guess those are the 2 objects being created here. Just so what are these data sets and data loaders? They are just coming from Torch Vision package, but okay, there is data loader. Data loader is coming. Oh, okay. Torch.utils.data.data loader. So the data loader is a class that's available in this, in this path, and these 2 are really handy objects, and you'll see in assignment 1 also. You will have to work with them. So what is the purpose of a data set? Data set, just think of it as a class which is just saying what is my data set size. And for example, if your data set is images, you don't want to load all the images at the same time into memory. Okay, so data set kind of indexes, okay, this file path is example 1, and this is a label for that file path. Okay, instead of loading it to memory, consuming RAM, and then saying, okay, what the label is, you can actually just leave it in disk. Okay, in that way, this data loader, which lets you create batches. Remember, if you're going to do gradient descent, you want to get a batch of data instead of like loading all the data and doing a gradient update. So data loader lets you create that batch by saying how to sample and so on. So that's why you can see there's some argument like batch size and you shuffle the data and so on. when you create the batch, it actually looks at the file path and actually reads that image and then lets you, where is this thing? Yeah, and then also lets you do the transformations and then therefore pass it to your model, forward pass. Remember, so data loader, when you sample a batch of 10 items, 10 images, then it reads from the disk, goes through the transforms, and then those tensors are ready to be passed through your network. So it lets you, so it's a handy object to instantiate and work with. So basically you'll do for loop over the data loader. And since data loader is iterable, you can put a TQDM around it, just like this that you see here. So this is the type of printout that you'll see with TQDM. Okay, so it's just a progress bar that will show, okay, how many things are left and how much, to do and so on. Here it's just downloading because we say, Torch Vision has a handy way to kind of download some standard images. So we are just downloading MNIST here, which you guys also did in assignment 1. But I don't know if you used PyTorch. I think you used TensorFlow there, which TensorFlow also has the same type of API. It's not exactly the same. And then defining a network, I told you, I think we saw it even like a quick PyTorch demo. So defining a network, generally you extend it from nn.module. Basically, there are two functions. One is the constructor function, which gets run when you create the object. And then the forward function, which actually tells like when you get an input tensor, how do I manipulate it to get a prediction? Okay, it could be a regression output, or it could be a whatever, a score value, basically the score that we talked about in lecture 1. So so basically here you instantiate the layers, and here you execute the layers, like call the layers, right? So they're very similar to, I don't know if you guys did the same in when you did the Keras example with MNIST in assignment 1, but it's a little bit more verbose than that. Okay, that because Keras is supposed to be supposed to make it easier than, a little bit easier than this. Okay, any questions here up to this point? Okay, yeah, so I think there's some execution still going on here, but let's see. Yeah, so here's a training function where I think I pointed this out a couple of times already, so may not be new information. So you can define loss functions. So just like in lecture 1, right? Loss function, a data set we just worked with. What's the model definition we just saw, and then finally the optimization step. Those are the 4 things. And then we just need to know how to do the optimization thanks to the behind the scenes magic by PyTorch and TensorFlow, right? So we define the loss function. If it's predefined, you can just instantiate it like this. If it's not, you can literally write the function. Loss function is equal to a minus b the whole square or something like that, right? So here, yeah, and this is a very typical pattern in PyTorch-based programs. You would then instantiate a optimizer. So there are many optimizer. Oh, sorry. There are many optimization techniques, even within the gradient-based techniques. So there's the SGD, stochastic gradient descent, which has the batch size and all that. And also there are other variations, something called ADAM, and then something called RMS prop. They're all slight variations of the same gradient idea. Okay, so just that the gradient update will slightly look different, but they have a popularity in terms of how they, there's a, it's empirical, but they have some different guarantees, give different performances that you can see. And so here we have instantiated ADAM optimizer. So typically a parameter is going to be learning rate, maybe sometimes more, and what parameters to optimize over. So so nice thing about nn.module, like if you create this network, right? So here we created that thing called net, right? Net is equal to whatever that class is, and then toDevice. And this is also interesting. A toDevice, you'll send it to the GPU if you have one available, or TPU in this case. Okay, so you will have to. So if you try to run CIFAR10, the assignment 2 question 1 in CPU, it's going to take hours. Okay, so I think you should try to see if you can get a GPU instance. Maybe next time we can see how to rent a GPU instance. But here you can certainly try to get GPU instances by choosing a change runtime type and trying to see which one at least are free. But you can also purchase if you want a faster execution and so on. Yeah. GPU subscription? No. No, not for collab. I mean, although which course it is and stuff like that, can you no, Capstone is a different thing. I don't know. Is it your sponsor providing it, or is the instructor providing such resources?
Like that's million talks, but it's like they don't even know how to build it. But they
Yeah.
are able to provide it.
No, I mean, this is like,
Like they're in a bit of technicality. Like
I mean, you can always rent a GPU even without doing anything. As long as you have a Google account, you can get a GPU. It's just that you won't get it for a long time, or you won't get the most powerful one.
there's always sponsor.
No, to go from free tier to premium tier is what you're asking. I'm saying that free tier is enough for your problem. So I don't know if you want premium tier, which is just I think $10 or per month or something. It's fine. I think not here, but you can increase your tier if you want more exclusive access or bigger GPUs or something. If you want access, currently it's not planned for the course. Yeah.
If a GPU on our machine, you can use that, right?
Yeah. I mean, but the GPUs on laptops generally are underpowered. But if you have a desktop machine with let's say, I don't know, RTX 3060 or something, which is not even the latest generation, right? 3 years old or maybe 4 years old. But if you have it, then yeah, that's that's actually great.
Is there like a separate course for like activity? I have that 3060 RTX. So I have to install Coda to build all those things.
Yeah, which is actually not complicated. So that's where Anaconda, if you've used Anaconda, you don't have to touch anything related to system drivers and stuff. Conda or Anaconda will let you install very easily the required things. Okay. So there are two things. So you have to have, so Torch requires some supporting package to be able to exploit GPUs. And obviously the system drivers, if you have an RTX 3060 or whatever, there should be system drivers. So that is external. That's just needed for gaming and whatnot. So there's some system drivers that you should install. That's just, but whatever you install, just don't mess with it. You install it once, right? But on the PyTorch side, it's pretty self-contained. Okay, today. I mean, it was not the case like several years ago, but today at least you should not be messing. You should not be able to, it's pretty smooth. Yeah. But the problem is with AMD chips, there are only a few AMD chips which support PyTorch today. Yeah. Or machine learning or deep learning in general. So anyway, so to device just means sending to a appropriate device. Actually, there's a nice logic here where you send it to either if GPU is available, if not, you just leave it on CPU side. But that's just a nice utility thing on PyTorch. But here's the loop, right? So this is where I'm saying if you apply TQDM on your iterator, then you can see the progress bar. That's what I think you see it here. This progress bar, that's what it is. But in all this, for example, here is a trace function, right? So this is how you set up breakpoint. So for example, you don't know what your data is. So I think train is being executed at the bottom. So okay, let me rerun it and see if right. So okay, let's actually see what the code is. So there's some notion of epochs. Epochs is like one pass over the data. And for each epoch, let's say I want to do 10 passes over the data. For each pass I want to iterate over this thing, which is the train loader, okay, which is the data loader where it picks a batch, puts into memory and so on. And I put a breakpoint, so we'll talk about the breakpoint. But then once you get the batch of data, this is just splitting it into two variables and then pushing it to the GPU if it's available. That's the 2-device part. And then you are setting the gradient. If at all previously computed gradients, if there are any, you set them to be 0. Okay, you're just setting the parameter. So remember, parameters have gradients, right? So because that's how you update the parameters. So if there are any, zero them out, and do the forward pass. This is the net or the model function call. Like it's just the model function call on the current input. That's what you get the output. You compare the output with the current labels, right? So that's cross entropy loss, and then you sum up the losses. If here I think it's a batch of whatever 10 different predictions. So you just sum the losses up, and then just some normalization. It's kind of not very important. And then this data iterator part is yeah, this is just to kind of track iteration limits. So that's just a helper code. So that's not essential. But the most important thing is loss.backward is the one which is computing the new gradients at the for the loss at the current parameters. And then optimizer step is actually making the parameters from old values to new values. Okay, the parameters of the net, the model. Okay, because optimizer knows what are the parameters, where the parameters are, and so it'll update it for you. Okay, these are the two steps, and you'll see the same pattern repeat at multiple places. Yeah.
So is it storing the old parameters as well, or is it replacing?
No, we are just getting rid of them. Yeah. Why you want to remember the old parameters? You can.
I mean, the goal was to remember all the parameters and get it.
No, the goal is to keep iterating. It's just stochastic gradient descent. So we are going from old parameters to new to new to newer to newer. We are kind of getting rid of the old ones.
We are just performing gradient descent.
Yeah, we're doing the gradients. So we haven't gone into LoRa yet, if that's your confusion. In LoRa, we'll kind of so this is just the usual gradient descent step. I don't know. Are you doing machine learning right now? Okay. Yeah. So this is just we're getting rid of the parameters. So we're just W new is equal to W old minus gradient of the loss with respect to W, right? Or theta new is equal to theta old minus. So theta old is gone. I mean, we are doing in place updates. So we're not really storing the old ones. It's not needed. What we're just storing is what is the loss at every time. So we should see the loss at least because we know the loss numbers, but otherwise we're not storing the parameters themselves. But although we do want to store parameters maybe after every epoch, it's like some sort of what is called checkpointing in the literature. Okay, checkpointing just means, I think I mentioned in the previous class, it's like saving at some game point, right? Something like that. Anyway, my objective is to talk about the debugger. So since I put a breakpoint essentially here, so the debugger, so we stopped right before we entered the for loop. Okay, so basically we are at epoch 1, 0%. Out of the 595 steps iterations in this epoch, we did not do any iterations. Okay, so in fact, if you want to, yeah, so at this point you can say, okay, data dot shape, right? It's not even a it's not a numpy or anything. It's actually list, right? So in fact, you should generally do type. I mean, this is not there's no recommendation here, but type of data is a list. So let's say length of data. We know it's a 2-element list, but you can check things. I know this seems very verbose, and there are better UIs like looking at variables and stuff. But I'm just showing you this is like a very versatile thing. PDB is part of the Python standard library, so it's available. You don't have to pip install anything anywhere. And so we know this. So for example, data bracket 1, since it's 2 elements, I think this one is a we know that data bracket 1 is like the y variables. So those are the y values. We know the batch size is 10. So this is a 10 cross 1 tensor. Okay, so you can see that it's a I think dot shape is not the right answer. Okay, this is something to test. Okay, I don't think that's the right function calls I'm making, but basically what I'm saying is you can investigate, especially if there is an error happened, for example, because of dimension issue and so on. Just put a breakpoint there and kind of get a sense of why the error is happening. Especially for dimensions, it's kind of easy to see that, oh, maybe I you need to change the ordering of the dimensions, with which there are some torch helper functions. I'll not focus too much right now, but there's a way to kind of reorder. Like if the first dimension is supposed to second dimension, then there's a way to flip them. Okay, and torch. Any questions here? And if you want to, you can press Q to quit. There's actually a nice way to navigate. I think / there's a way to. Oh, it's not showing here, but you can press Q to quit, exit this debugger, or you can continue by pressing C, or you can step one by one. Like it's very similar to any other debugging practice. Like if you want to step line by line, there's a way to, if you press N, then it'll go to the next step. And the next step is these two variables are initialized. So you can look at what is the num underscore iterations value now. Okay, it's it started with 0 and added a 1 value, so that's why its current value is 1. So you can step one by one and get a sense of where, what's happening in your code. Okay. Any questions here with the debugging? Okay, let's quit the debugging. And now let's come back to our LoRa step. I just wanted to point out PyTorch related things because it's going to be helpful for your assignment. I wanted to briefly talk about debugging because that's also helpful for your assignment and subsequent assignments and project. Now let's come back to, is it gonna, okay, let's actually, oh, I quit. So, okay, that's fine. So I hope the model did not change too much because we didn't really do anything. Okay, so so what are we doing now, right? So let's come back to LoRa, right? So as I said last time, and we have a diagram, but I think I will skip showing the diagram, but it's basically, if you have a W matrix, and there could be many W matrices, if you have multiple linear layers, there could be many different W parameters, okay? But for any given W parameter, the way we are doing this transfer learning or fine tuning is that the original models, W is kept as is. And then we have an extra W hat, which is the inner product of two thin matrices, okay? One tall matrix and one wide matrix, okay? Why is it tall and why is it wide? Their product should be the same dimension as the W matrix, okay? So A times B should be the same as the original W matrix, but A is tall and B is wide, which means that they rank the second dimension. For example, A, the number of columns is going to be something very small, like 2 or 3 or 5. Okay, number of columns of A is going to be small. Number of rows of A is going to be the same as the W. Number of rows of B would be 5. Let's say rank is 5, and number of columns of B would be the same as the original W. Okay? So that the product is the same dimension. Is what I'm trying to say. Now, so for every W, we'll have a couple of matrices like this. And these parameters are the ones which we're doing backprop on. The original W parameters are frozen. Okay, that's all. That's the only difference. That's what we're doing. And when we do backprop, we have our new data set. So obviously there will be some losses. And we are adjusting the parameters of this A and B matrix only, not the original W. Okay. So what does the forward pass look like? So if there was an X being coming as an input, and then WX was the output, now what's going to happen is X is going to be the input, and W plus A times B times X is the output. So it's just additive. Okay, so it's just, it's just conceptually saying that, oh, originally if there was W, now you have a W plus A times B, because W plus A times B makes sense because of the same dimensions, and that times X is what is going forward. Okay? So that's the idea. So that way, it's actually a very, very nice idea. Helps to have a strong base model, like a foundation model, like a foundational LLM, and then you can adapt it to maybe medical text, or maybe to law related text and so on. And that information, those patterns can be only part of, you can make it such that they're only part of this A comma B type of parameters, so less number of parameters, and so you can have multiple adapters to the same base LLM that was trained. Okay, and a lot of people have done this on all these LLMs that you've seen, like Llama and so on. I mean, if you've not seen it, that's fine. We'll talk about LLMs in a later lecture. Okay. Any questions here? So the rest of the code is just showing, I just ran this code. It's just showing some performance. It's like the diagonal matrix, so diagonal entries of, or the off-diagonal entry sum of a confusion matrix. So it's an MNIST problem. So it's like a 10-class problem. So you can see how many times did I, mistake 0 to be something else, mistake 5 to be something else. You can just add up the number of counts, and that's what the counts are. And then you can say, oh, okay, what if I add the original number of parameters in this network were 2.8 million. Instead of that, if I added this LoRa, the A comma B, there'll be another 6,000 or so parameters we saw last time. And then we are only tuning on those 6,000 parameters with some additional data set. Okay. This is just an illustrative code. So this is not exactly doing any improvement for MNIST, because MNIST already, you don't need deep learning. Actually, even you can use simpler models to kind of have a really high accuracy there. So, but this is illustrating how to do LoRa. And this is not the only way. You can write it in multiple ways to achieve the same thing. The idea is just that you have this matrix approximation, additive matrix low rank approximation to or the original weights. The original weights remain unchanged. You have additive W hat, let's say, and that's product of two thin matrices. Any questions here? Okay, so let me then not get into all, I mean, because there are many ways to achieve the same thing. This person used this parameterization. Yeah, there's a, in the utils, nn.utils, I guess, sub root, there's a parameterized routine, which lets you achieve this lower thing, but you don't have to write it this way. You can write it in many multiple ways. So I'll not focus too much on this. Okay, if there are no questions, then let's get back to our slide deck. Okay. So what I want to do now, I know we saw code, so I hope everybody is not exhausted. We'll look at three things: data augmentation, weight initialization. There'll be just a brief commentary on it. But we'll look at data augmentation, batch normalization, and dropout. Those are the three things. Okay. So, and by the way, all of them are kind of straightforward ideas, nothing super complex, very natural things that even anybody in hindsight it seems very kind of straightforward. But it was a good good ideas when they came about, and they kind of become standard. It's a good idea to try them if you can. Okay, so data augmentation is related to the transforms line that you saw. By the way, we were normalizing input data. Instead of that, you can do some additional things. So yeah, I mean, I was saying there are a few empirically validated techniques that we'll see that kind of stabilize the training of not just CNNs, but other neural networks also, and also help improve performance. We'll look at a couple of these, which is data augmentation, batch normalization, and dropout. Weight initialization is just a commentary. We will not talk about optimization actually. So there are the Adam thing or the RMS prop or SGD. There are multiple choices there, but we'll not talk too much about it. Although most practical, like a good way to also improve perhaps learning or to control learning is to kind of work with the learning rates, because the bigger learning rates, if you remember, your iterates will be bigger, and so you may be like jumping around. Whereas you use really small learning rates, you may not be able to. You may have to take so many iterations to get somewhere. So there is that learning rate aspect that is also seems important empirically. Okay, so let's look at data. There are multiple aspects of data, and actually they're, I think, maybe more relevant to the MLOps course, but they actually companies around how to efficiently store and transfer data for images, especially how to work with them. Okay, because this is images are actually pretty heavyweight objects, especially, I mean, maybe for CIFAR 10 and even CIFAR 10, you'll see that they're heavyweight objects when you do the assignment. But MNIST, it's like, okay, you can literally load them up in memory and there's no issue. But really storing them and processing them is a pretty Herculean task if you do it naively. Okay? And so there are companies which actually optimize the location of images, so they're right next to each other in terms of on the disk, so that the disk, you don't have to jump around disk sectors to read them. So there's that aspect, which is too low level, maybe it's more software engineering. There's also obviously statistical aspect, which is quality. So get your data clean. Hopefully no sensor issues, no occlusion issues, and things like that. But also no labeling issues. Hopefully there are no errors in the labels and stuff. Okay. So those are all aspects that are important for the performance of your whatever model you're building. But let's say all those are you've already considered. Here's a new idea. So the idea is very natural for images. So let's say you had an image pair X and Y, image and label pair X and Y, and obviously Y is used towards the loss directly, and then X is passed through a huge sequence of collection of blocks, and then you get some score, and then you can check whether your Y matches the score or not, right? The idea is basically to kind of change xi to some other x tilde I. Okay, so how do you change images is what we'll see, but it's a very natural idea. So it's like saying, oh, if for this image, if this is a label, then if I slightly change the image, it should be the same label. That's a natural idea. Okay, And that leads to what is called augmented data, right? So now instead of having 1,000 examples in your data set, you could have maybe 2,000 or 5,000 examples if you do five perturbations of per image. Okay, so you just scaled up your data like anything. Obviously, the data is like not very different from each other, but still it provides some good relief in terms of you don't have to kind of you can take advantage of now a bigger data set to kind of train your model. Okay, so what is X tilde I? It's just some deterministic or potentially randomized transformation of your original image. Okay, and what are these transformations? Here's an example to kind of drive home the point. We can change the input, right? And we add this new example to our train set. What are the types of changes? You can change the colors. I mean, that's not always, appropriate, but sometimes you can change the colors, numbers in the pixels. You can flip the image sometimes. You can randomly crop the image. Maybe, maybe part of the image is still able to predict that it's a house and not a airplane, for example, right? And you can do all sorts of sharing operations. You can stretch on one side or stretch, in a different direction, not just left, horizontally and vertically. So you can do many things like this. And this is not even the exhaustive list. And there are many, many options available in PyTorch and TensorFlow that you can try. And so this is a way to augment data. Okay. And you can also augment data at test time. So in the sense inference time, maybe you already have a pre-trained model. Now you have a test image. Instead of just passing the test image and getting the label, you can pass the test image, a cropped version of the test image. You can you can share the test image and pass it so that you can get many, many, many predictions for slight variations of it, so that you're a little bit more confident, perhaps, in like saying that it is the object X or Y or Z, right? So here, I mean, in the ResNet, which is actually the model that you're going to use in assignment 2, the full ResNet is not ResNet 18. It's called ResNet 50, I think, with 50 layers. So it's pretty deep. But that's actually the winner for ImageNet recognition in 2015, 9 years ago. And that was actually using this idea. So it was actually taking the image, creating 5 scale, 5 images from it of different scales. And for each image, at each scale, it was actually doing 10 crops. So a lot of actually, I guess at 224 you can't really do 10 crops, but at other ones you can do multiple crops. Okay, you can do top left, top right, center, and all sorts of things, which is what it's showing here: top left, top right, some center crop, and things like that. Yeah. Any questions about augmenting data? So this is a very simple idea. I mean, in hindsight. And it can also be implemented without too much coding. In the transforms line that we showed, there was a transforms.normalize. You could call transforms.random crop, transforms.horizontal flip, and you can just get these for free. Yeah. You had a question?
So I'm just a bit confused about this by cropping. This is the same as the previous slide you showed where we were randomly cropping the.
Yeah, this was just so this is not 5 crops, right? So they were just, this is a choice that ResNet made. This is just an example that in ResNet, during inference, even if, irrespective of how, whether data augmentation was done or not during training, I mean, they might have done it. At inference time, they were just doing, given in a test image, they would scale it to 5 different scales. And then for each scale, they would do not random crops, but like these types of specific crops, and then do a prediction, and then aggregate the prediction to get the final prediction. Yeah. But yeah, data augmentation generally means augment your data by doing some transformations. The moment you do at least one transformation, you have doubled your data. Okay, effectively. I mean, it's not exactly independent and separate signal, but it's it strengthens the per class data availability. Yeah, so you can mix all these translations and colors, all sorts of distortions. Very useful for small data sets. So I think now it has become standard practice. By default, you would kind of do some of these data augmentation steps. But of course, be careful about certain transformations. Certain transformations don't make sense. For example, for MNIST, you can't flip the images. You can't flip 6 and 9. Like if you do a vertical flip, then you're like messing up the 2 classes, right? So yeah, just need to be aware of that. Yeah, let's not worry about the second point of view. It's just some food for thought. But any questions about augmenting data? Okay. So then let's talk about, so that, these innovations or these extra ideas. First one was about data. The second and third and fourth will be about models. Okay. In fact, a quick commentary on weight initialization. That's not really a model specific thing. It's more about optimization. So we've already seen a lot of ideas about model definition, right? Like activation function. Nonlinearities is what brings more interaction in the feature space if you don't do feature engineering, right? So we saw that in the playground.tensor.org example, where we either explicitly did feature engineering to do that two-class classification with like a circular decision boundary, or we had just the two features, but we did like a 7-layer model, and then somehow we got the circular decision boundary, right? I mean, if you recall from the recordings. So we have seen some choices that we need to make already, and there are a few more, not really choices, but a few more mechanisms that you can add in. Okay, a few more knobs that you can change to potentially train them more stably, more easily, maybe get some performance improvement also. One of them is about the optimization part. Actually, it's not really model, but the other two are interesting ideas: batch normalization and dropout. Okay, so it's just a brief comment about weight initialization, although I put it on a model, but it's more about, initialization has an impact. So it's something, if you think that, although there's not much you can, at least naively, this seems like we can't do too much, right? We can just say numpy.random or, or numpy.uniform or Gaussian or uniform or some kind of popular choices. And beyond that, it becomes nuanced, like, okay, why is some choice leading to some model eventually, some model performance versus some other choice leading to some other performance. There are folks who study this actually, very nuanced of, okay, maybe some parameters I should initialize as uniform, some parameters I should initialize as, maybe Gaussians or gamma or some other distributed values. That's because the weights where you start influences the gradients that you get, because clearly the loss is a function of the current weights that you have. And so, I mean, we saw this diagram before, where obviously where you start influences where you get to, depending on like if you start here, you get here potentially, and if you start here, you get there. But not just that, the iterates also get influenced, because clearly the weights are going to be part of the gradient values themselves, right? Unless it's like a linear function, then maybe weights will not be there. So, and because they're part of the iterates, they'll also influence the activation statistics and all sorts of things that you'll see during the iteration. So there are some heuristics. I won't even name. They're actually named heuristics. There are names for these heuristics, but I won't get into the detail because that's like beyond the first level choice of choosing between uniform and Gaussian and maybe all zeros and things like that. Once you hit some, if you think that that's the area where you think there could be some bang per buck, then it's good to go into the literature and see what people have studied, because people have done some extended experimentation on what could be good choices. Okay, so that was just a comment on weight initialization. So let's really talk about the next two things. The first idea is called batch normalization. Okay, let me. Yeah, so last time we saw this app called Netron, right? Okay. Right. This was just an app which would visualize neural networks. So I think I just wanted to kind of open up the same model, which I now kind of don't remember. Let's see if this is the model. So if you look at this model, right? So this is just a visualizer for the network. It's the same thing as printing out layer by layer. What is the dimension? It's just a more visual, nice looking graph. So you can see there's a green step here between the column layer and the non-linearity actually. So it's being inserted between after doing the filter operation. And after doing filter operation, you can get one number, that's a neuron, and you're not directly immediately applying a non-linearity here. Okay, you are doing a step called BatchNorm, and that's what we're going to study. Okay, this is the network called you only look once, YOLO. Okay, I don't know if you've heard of it, but it's a very nice pre-trained model that can be used to do. It was trained on an 80 class classification problem. So it can detect pedestrians and people and cars and all sorts of objects. It's part of it's trained on a data set called MS COCO. It's for object detection. Put bounding boxes around images. Image is an input. You find objects of interest. Okay, so that's what this model is. It's called YOLO. And you can see that at the beginning of this model, you have a BatchNorm, right? So not just at the beginning, but actually anywhere I think where you use conv layer, there is a BatchNorm involved, and so that's why we're studying. And this is one of the popular categories that works even in 2023. So it's good to know what it is. And this is not the only place. There are many places you have BatchNorm. So what is one, at least one motivating angle here is that activation, and just like from the previous slide, we said, where you initialize, where you start the weights from to kind of do gradient descent influences the activation statistics. By activation statistics, I just mean what are the values of the activations of the neurons, different neurons that you see, right? So these activation magnitudes depend on the data set, the network, and the nonlinearity used, and obviously the gradient descent scheme used also. And these statistics are, you can say that either they influence gradient propagation or they are like an artifact of how well the gradients are propagating. I'm not saying, although here the statement says it's influencing A, influencing B, but all I'm saying is the activation statistics are kind of a way to understand, like, are gradients actually even flowing or not, right? For example, a simple way is if there are a bunch of dead ReLUs, they're never producing an output, if their output is always zero, then you know that the activation statistics there is like all zeros, a huge spike at zero, and then some non-zero numbers. And so then you know that gradients are not propagating there, right? So are not propagating back from there. So the kind of one of the angles for kind of doing this batch normalization step is to kind of somehow recenter these activation numbers. Okay. So what are we doing? So think of a layer to layer to layer to layer. There's activations that are generated, which is basically neurons outputs after every layer operation, right? You're basically just recentering them in some sense. So if you have done the z-score type of operation in IDS 570 or something like that, you're just recentering them. You're subtracting the mean, dividing the standard deviation. Effectively, that's what we're doing here. Okay.
And explain the centering.
Yeah, we'll see the centering in the next slide. So yeah, I mean, recentering the numbers means it's just a rescaling. Okay, so in scikit-learn, for example, you have scalars, right? Standard scalar and all sorts of scalars. So yeah, here z-score operation is also the same thing, right? If you have a number, you subtract the mean of, if you have a bunch of numbers, you subtract the mean from each of the numbers and then divide by the standard deviation of this collection of numbers, right? That's like centering the numbers to be like zero mean and unit variance type of data. Yeah.
You're talking about standardizing the.
Yeah. That's what you do in other situations. Yeah, this is batch normalization. The normalization is basically kind of the same idea. It's trying to standardize these numbers, like shift the. So what are we trying to do is from layer to layer, there are some original activation values, which could have, like, let's say the values are between -100 to 5,000. Okay, some on a very lopsided distribution. What we're going to do is like standardize, as I said, such that we'll have numbers between, let's say, -10 to 10, and like some zero mean unit Gaussian, or maybe some variation like that. We're going to recenter the numbers and then pass it to the next layer. Okay. In fact, we will not directly pass it to the next layer, as you saw in the illustration. Once you recenter the numbers, then you apply the nonlinearity, and then you pass it to the next layer. Okay. So what is that? So normalization just means exactly standardization or scaling stuff that you do. The batch part just corresponds to the fact that this normalization happens across the batch. Okay, it's not each individual example does not get normalized by itself or anything. So there's no neuron 1 to neuron 2 comparison going on. It's the neuron 1 across the batch comparison going on. Okay, what do I mean by that, right? So think of this. Think of feed-forward network. So let's say we have a batch size of n. Okay, so let's say n is 10, for example. In our previous code, batch size was 10. So let's say batch is 10, and let's say the number of output neurons is d. Okay, so d would be the number of columns, and number of rows would be the batch number of batch size. Okay, so what we're doing is looking at one neuron but that neuron's output across the batch. That's what I'm kind of just highlighting here. Same neuron across the batch, what are the numbers it's produced? Okay. So if the same neuron across the batch produces a bunch of numbers all over the place, I want to standardize it. Okay. How do I standardize it? I just do a subtraction to expectation and divide by the variance of those numbers, these numbers. And then the standardized numbers are just filled in place or whatever, like a transformed output there. Okay. So, what is the standard operation? Standardization operation x minus expectation of x divided by the square root of the variance standard deviation. So it's the same kind of standardization that you've seen elsewhere. It's just that it's happening across the batch.
Let's suppose say that since we have divided our total data into multiple batches, right?
Yeah.
Even if it's randomized, it's possible that the overall magnitude of one batch is considerably higher than the magnitude of other batches.
Yes.
And when you normalize them, essentially they would come to the same level.
No, the magnitude. So we are normalizing that batch is average.
Yeah. So exactly.
Yeah.
For example, let's say we have a series of numbers from 1 to 100, right?
Yeah. Yeah.
One batch has the numbers 1 to 10.
Yeah.
And the other batch has the number 90 to 100.
Yeah.
So when we normalize each of them,
Yeah.
essentially they will have the same magnitude.
Yes.
So wouldn't that?
But that's what we want to do with this batch normalization business. We want to kind of, have similar activation statistics.
We don't give weightage to each individual batch size.
No, I mean, you can add such things if you want. But yeah, we want to kind of make it batch independent normalization. So whether you're part of batch 1 or batch 2, the two batches that you said, you kind of want to have activation numbers look similar once it's processed through whatever is the layer that you pass through. So even whether you are 1 to 10 in one case or 90 to 100 in the other case, you're basically recentering, standardizing, right? So yeah, standardizing is actually killing the difference that, okay, one was 1 to 10 and the other one was 90 to 100. I'm not saying it's always desirable or anything. I'm just saying that's what it does. That's what this does.
I just had a thought that, for example, if we are predicting whether a person will be able to pay back his loan or not, right? Just a simple example.
Yeah.
So let's take the same example, 1 to 100. And that's the income of a person, right? So 1 to 10, less likely to pay off the loan, 90 to 100, more likely to pay off the loan.
Yeah.
But once we have normalized them, the result could be similar of both. Which
no, I agree.
Essence would not be the right thing to do.
Yeah. No, I agree with you. For that, here we are working with images, so it's not exactly the same situation. But actually, there is this notion of, that's why in the name ResNets, there is a residual res part. Res stands for residual connections. So there are going to be, I don't know if there is actually any model. So you're saying, yeah, what you said is correct. If you do BatchNorm in your example, we are kind of ignoring that income levels, for example. So this that you see, for example, here from the previous column layer is actually a output directly is skipping over all these transformations. So you can imagine if this was the input. Let's say this is the input. From input, you're doing BatchNorm. So as I said, things get recentered and we lose the signal, that income level signal. You can imagine the input is, in this case, you can see the input is going skipping again. So there's two parallel paths to the next computation, right? So this is called residual connection. In fact, this is why the name residual or ResNet comes from. Okay, so this whole skipping process up to some point. I mean, you can see that here there's some BatchNorm happening. So this may not be a good example here because this is for images. But if you imagine the skip connections are what will retain some of the information that you're talking about. But yeah, I'm not saying BatchNorm is needed for every network. But the intuition is, this is the intuition, to recenter the activation statistics so that your gradients actually backprop. Because otherwise, if the numbers are lopsided, you may get zeros, max of 0, x or something, it'll become zeros, right? So here, if you can see that BatchNorms are also are applied before the nonlinearity, the leaky ReLU that you've already done in assignment 1. So you're recentering the numbers so that some numbers are negative, some numbers are positive, and therefore you know that there will at least be some neurons which will be which will produce non-zero numbers. Okay, but if you did not apply BatchNorm and if the previous numbers were all negative, then this output is 0 here, and so no gradients will pass, right? Yeah, but you raise a good point. Yeah, and so but when you do BatchNorm, although here it seems pretty simple to kind of in terms of concept, behind the scenes there's always this question of batch versus batch variation, and do I recompute these expectations, or can I have a moving kind of can I keep them in memory, or some sort of have a running sum or running weighted average or something across batches, so that these numbers are not changing too much perhaps. And then there's also the issue of that's during training, but also the issue of at test time, there's not going to be any such numbers. Let's say you only get one image, so there's no batch. So where are you going to get these numbers? So you probably remember these numbers from training so that you can actually subtract, because otherwise your whole processing is like different, right? At test versus training. So there are some nuances like that. But these packages like PyTorch and TensorFlow do take care of these things behind the scenes for you. Okay. But this is where the balance is, like, you should know what's going on behind the scenes, some of these function calls. Otherwise, you may be doing something which is not like appropriate. Like in your loan example, it may not be appropriate to even apply BatchNorm, for example. Right? Any other question here? Okay. So yeah, here, yeah, this is basically that figure for YOLO submodel. So here con BatchNorm and then ReLU. But you can incorporate those. So BatchNorm you can incorporate anywhere. But generally this is where we have seen it used. Yeah, and empirically, what's driving it is basically with the BatchNorm fix, you can have deeper networks and gradients can still flow back and forth, and you can actually have stable learning. Okay, the whole challenge with deep learning, even 5 years ago or 10 years ago, was that the moment you add even 4 layers, 3 layers, 4 layers, 5 layers, it's very hard to train. Okay, somehow the industry has figured out, okay, there's some ways to train by appropriate initialization and adding these types of things. We can actually have deep networks, and which means they're richer networks, and so can capture much higher variability in the data. And that's why you can see amazing inventions like the language models that you're seeing today. Okay, the next idea is called Dropout. I think let's take a 10-minute break and then we'll come back to Dropout. Yeah. Okay, let's resume. So before the lecture, before the break, we saw data augmentation, weight initialization, and then batch normalization. The last, one of the I guess last ideas in this basket for today is the idea of dropout. Okay, so previously we've seen L1 and L2 regularization, right? So why, just to recap, right? Regularization is an important topic. I know we kind of spent one slide on it in lecture 1, but it's a way to control the complexity of your model. Okay, and these models naturally are very complex. Okay, the moment you have fully connected layers, like for example, the MNIST case in the LoRa example, you have 2 million parameters, right? So does it make sense to have 2 million parameters when your number of features is 700 and maybe you have like 10,000 data points? Obviously MNIST has more data points, but like all I'm saying is if you have 10,000 data points and you only have like 100 features, the size of the data is like much smaller than the number of parameters. Okay, so like by just raw counting, so you have to, at least for deep neural networks, it becomes important to kind of how to think about how to control the complexity of these models. Okay, so one of the ideas there is called dropout. So the idea is also, it's a very interesting idea and actually pretty prevalent even today. So a lot of people try to use dropout to kind of restrict the complexity. So its purpose is going to be very similar to the purpose of doing L1 or L2 regularization on the weight parameters. Okay, so we saw L1 and L2 before. So what's the idea, right? So the idea is every time you do a forward pass, you're going to randomly drop some of the neurons. Okay, what is meant by dropping the neurons? We're going to set the neuron output to be 0, irrespective of whatever the output was. Okay, while doing further steps in the forward pass. So for example, think of a layer. Let's say the layer has 100 neurons, 100 dimensional output. Let's say simple fully connected layer. 100 neurons are produced as an output. If we say dropout is 0.5, then every neuron with 50% probability will set the output to be 0, irrespective of whatever the current output was. Okay, we'll set the output to be 0, and then those numbers are now forwarded to the next layer. Okay. So that's the mechanism of it. That's just a mechanical explanation of what do we mean by dropout. We are just dropping out some numbers that we computed. We're just removing them while trying to make the predictions, which is while producing the score values. Okay.
Like you mentioned, 0.5 and
Is this a parameter, just a choice?
example.
Yeah.
So it's like the output out of for example, when we take the max function to convert it into probability.
That's later. That's the output. So let's look at this example, right? We have seen this one hidden layer neural network before. Sorry. Yeah. So we have 3 inputs, and let's say we have 4 hidden vectors. 4 hidden values. So 4 neurons, and then 2 outputs. Okay. So it's a binary case. So all we're saying is, without dropout, this is the forward pass and this is the backward pass. So all paths are kind of valid. In a dropout case, one of the passes, I mean, not every pass will look like this, but one of the passes, you could just say dropout is 50%, maybe I drop the first and third neuron, which means that its output is 0, which means that it's not affecting anything. 0 plus anything else, let's say there's an addition or something, it's not going to change anything, right? So what you're saying is, for the current input, you compute these neuronal outputs, these 2 neuronal outputs. Those 2 neuronal outputs should be driving the score vector, pretty much. Okay, so the score should be still, you want to ensure that the score, let's say the true class is the first class, then you want to ensure that the score here is higher than the score here, so that you can classify correctly. But that score is only dependent on a smaller set of neurons. Okay, not just in its preceding layer, but it could be, dropout could happen in multiple layers. So all through those layers, a lot of things are getting dropped out. So a very small, so a score value is only driven by a very small, a tree of like whatever, previous computations, and still it should be the correct answer. Okay, so basically you're massively reducing the capacity of your network effectively. It's as if your network is no more the original network, but really all the things where the dropout was 0 are basically you've weeded them out from your network, and you just have a very, very, very kind of sparse network. Doesn't have to be very sparse, whatever, but you just have a remnant network now. Okay, so that's the idea of dropout. Any questions here in terms of what's the mechanics of it? Okay, by just understanding them. Yeah, by just understanding the mechanics, you should be able to appreciate like why it's reducing capacity. It's like obvious, right? If you have a score that you need to produce, but you need to only use a fewer number of neurons than all the neurons that were in the definition, then that function, that is the remaining function, it's not high capacity anymore. It's less capacity than the original network, right? Clearly, in an intuitive or a qualitative way, this network with two nodes removed is going to be somewhat simpler or less complex than this network, right? So that's what is happening here. We are reducing the complexity, and that's what we want to do. So why do we do regularization? We want to bias our model or our results to be not just dependent on data, in the sense that we don't want to overfit on the data, right? We want to get away from overfitting the data, and that's where you can see that by reducing capacity, you are going to be not, overfitting on the data. Okay. Any questions?
And so, since we are removing, so is it necessary to remove the ones with low probability, or can you also?
No, it's just uniformly at random with some probability.
It's at random.
Yeah, uniformly at random with the fixed probability is what people do, but you can do all sorts of variations if you want. The only complexity is you do want to track. You do want to keep track of dropout probability, for example, because if your network is trained with dropout, that means that some sort of aggregate magnitudes of the numbers, like the layers expect is going to be of certain magnitude. And if you at test time, if you don't drop out, the magnitude of the numbers is going to be more. So you do want to kind of ensure that you're not doing something wrong. Okay. So you do need to track. So it will not be dependent on probabilities. Like even if I, let's say, uniformly drops, which means that I flip a coin, this one says drop, we drop it. I flip a coin, don't drop, flip a coin, drop, flip a coin, don't drop. Whatever is the coin flip probability, let's say 0.5 or 0.3, whatever it is, that number is going to be useful later on when you already learn these weights and bias parameters, let's say in this 2-layer network. That probability will be useful while doing a forward pass at inference time or at test time. Okay. Any questions? Yeah, in fact, I'll come back to the probability thing. So intuition is basically we are making use of smaller capacity of the network. So the full network was the canonical network on the left side. Now we want to use a smaller subset of the network, basically the smaller graph, computational graph, effectively. It's not really a computational graph, but the smaller illustration to kind of predict. So that's why you can think of it as a regularization. It's using a smaller capacity. And it's also forcing some redundancy. So it's making all the neurons to be useful. So if it happens that one of the neurons is very critical for making the prediction, if I drop that neuron, it's not like it's not like you can just fail, right? So at test time, at training time, you're trying to ensure that no neuron is extremely critical. So there is redundancy in like a signal, and that's again kind of way to say that you're reducing capacity in the network. If there's going to be redundancy, that means that it's not going to be very rich. Every neuron is not going to be unique in some sense. Okay. Another point of view, which it's not going to add too much, is that it's as if we are subsampling the network. So you can think of this as like a sample of the full network, where we drop these two, so it's a subnetwork of this network. And so every time you do a forward pass, you're looking at a subnetwork to do the forward pass. Okay. So you're looking at subnetworks to do the forward pass, then when you don't drop out, it looks as if you're doing an aggregation of all these subnetworks, which is the full network. But the aggregation doesn't exactly map out like that, because the aggregation will have, is it equally weighted or what it is not clear here. But you can think of it as like an ensembling of all these subnetworks, which gives you the original network potentially. And so that is also adding to some robustness. If you're, it's like a majority vote of multiple networks. It's like random forest, right? You're looking at parts of the data and trying to predict the same thing. It's something like that in analogy. It's not exactly the same, obviously. But the core idea is regularization. Really reduce the capacity so that there is redundancy, or reduction in capacity. I mean, redundancy is just a byproduct of that. Okay, so higher probability means obviously stronger regularization, because you have a much smaller network to make the same score prediction. At test time, you could do one thing, right? So if you wanted to retain the dropout, since you did drop out during training, you could say, okay, I'm going to take the same input, maybe 100 times I'll do a forward pass, and in every forward pass I might drop out different neurons. That way, at least, I won't have different numbers or different statistics at every layer. So you could do many passes, or you could do some sort of correction to magnitude of the numbers that you're getting. Okay, so which means that you could do no dropout, and then you could scale the activations by the probability of the dropout. What do I mean by that? So that network that we saw with the two W1 B1 W2 B2. So let's say we did the dropout with probability P while training. Then this is the original network, right? So W2 times max of 0, W1 plus B plus B2. Then with dropout, at test time, we could do what we need to do is introduce the T parameter. So when we do W1X plus B, max of that, we'll get the activation for all the neurons. All the neurons are there. Instead of explicitly dropping out with some random probability, we'll just scale all that vector with a fixed parameter p. Okay, so that the magnitude of this, so p times the full vector is as good as saying without p only some entries, because in terms of magnitude you kind of will get the same magnitude of the vector. Okay, and then you do w2 plus p. So all I'm saying is that this is again done behind the scenes for PyTorch and TensorFlow for you, but this is some correction that you need to do at test time. Okay, just like batch normalization, there's some correction you need to do at test time because there's no batch to normalize during test. Yeah.
So the last time will only perform at test time.
Which one?
The W2 times P.
Yeah, this addition of this extra scaling factor you do at test time because you want to kind of match the magnitude of vectors or magnitude of the numbers that you're computing similar to the training time. If you use a dropout of p at training time, you would use the same parameter p here. I mean, you would not explicitly do this. I mean, TensorFlow will take care of it, or PyTorch will take care of it. But if you look at their source code, that's what they do. Okay. Yeah. So what we'll do is let's look at an example. This is a link on the lecture goals page. So it's just a link. It's called overfitting and underfitting, and this is where I'm just introducing this because we did talk about regularization. So it's good to kind of get a sense of underfitting or overfitting, which you have seen probably in ML or data mining or other places. So this is actually TensorFlow, not PyTorch, but the ideas remain the same. So this is actually the example data set. Let's not worry about it. It's called Higgs data set, but it's a 28 features and a 2-class problem. So it's a 2-class classification problem, binary classification, and it has a lot of examples, 11 million examples, and we are building a 2-class classifier. Okay, so what this script, and this is just a notebook that we can open in Colab. There's links at the top actually for running it in Colab and looking at the code and so on. I'll not run through Colab, but and I'll also not talk about details of TensorFlow because we already, PyTorch is already API you want to learn. So I don't think learning 2 APIs at the same time is a good idea. But if you want to learn both APIs, that's fine too. So it's a 2-class classification problem. I want to just appreciate the overfittingness and underfitting issues, right? So we are just showing some features as some plot of the features, but let's actually directly go to the demonstration of overfitting. Okay. Obviously, simplest way. So we care about overfitting and underfitting, but we have to start somewhere. So let's start with the simpler model so that we know that we're not going to overfit and slightly kind of make the model more and more complex and see that are we actually overfitting, right? So that's the idea here. So this is just a description of what overfitting is. So let's get to the plot of what is the performance of some size model and then the bigger models than that. And there's a tangential mention on this aspect that I mentioned earlier, right? So this is a plot of learning rate as a function of epoch. And here they're actually changing the learning rate as a function of epoch in a certain way, right? So this is another knob which we have not talked about, but influences the performance of your model. So at the beginning, you want to have large learning rates. So because you could be at wrong, the weights are completely irrelevant, not very informative. But as you get closer and closer, as you've done more and more epochs, maybe you want to kind of not be very jumping around. Maybe that's you've already hit some sort of local minima, and so you want to kind of really hone in there, right? Anyway, that's a tangent. But let's come back to the models. Okay, so we'll not look at the code. So don't worry about the code. We'll just say. So the first model, I think they call it the tiny model. It has 400 parameters. It's just 2 dense layers. Just means 2 fully connected layers. With 464 parameters one of the layers, and second layer is 17 parameters. Okay. So anyway, so 2 layers, and this is a plot. This is a typical plot that we'll see. Okay, it's a 2-class classification problem: cross entropy loss versus epochs. And so the tiny means the tiny is the name of the model. Training and validation curves are the solid lines and the dashed curves. So you can see that cross entropy loss is higher in the validation set and obviously lower in the training set, and this is a function as a function of epochs. So you can see that there still is some decreasing trend, and we could probably further decrease it. But it's a lot of epochs, 2,500 epochs, and typically one epoch means one pass through the data. So it may be quite a bit. Okay. Now there are some other models that they've also defined, like small model means a few more parameters. Now it's 760, like one more extra layer. Similarly, they have other models like medium, where they have added like 2 dense layers or 2 fully connected layers. Now it's a depth 4 network, and they also have a large. Sorry, let me just go back. Yeah. They also have a large where they have like 6 layers. Okay, so they have increased the number of layers quite a bit. So and what they want to see is what they show is the following. Okay, let's appreciate the graph first, and then we'll go back to some conclusions above. So again, so basically every pair of colors is like one type of model, going from blue, which is the smallest model, to a little bit smaller, a little bit bigger, and really big. Okay, and you can see this deviation from dashed line, which is like trending up. Okay, and these solid lines, which are actually trending all the way down, which means like they're overfitting quite a bit. Okay, so cross entropy always zoomed in. Okay, 0.5 to 0.7 is a big range for cross entropy. But you can see that within like about less than 100 epochs, okay, x-axis is log scale, less than 100 epochs, you're actually orbiting like quite a bit here, okay, compared to your blue line, which is fitting, but you are almost like 2,500 or maybe even more number of epochs. Okay, so so I'm trying to point out 2 different trends, right? So for the tiny model, these 2 curves are close to each other, and which is a good thing generally. And for the largest model, the validation loss has gone up. Okay, if you are tracking this, you know that you're like completely off here. You're just orbit like anything. So you could probably stop. You will say, okay, maybe stop here. But these models have lower validation loss and lower training loss, but at the expense of like so many iterations over data. Okay. So there's actually a nice blurb about some conclusions. So it's normal for there to be a small difference between validation and training curves. Second point, I mean, this is just by the way, very empirical. It's like rules of thumb being described here, some observations. If both metrics are moving in the same direction, probably you're fine. If the validation metric begins to stagnate while the training metric continues to improve, either it curves up or validation is flat, but your training is going better and better, then you have a problem, right? So you are kind of close to overfitting or overfitting. Obviously, if your validation metric is not even stagnant, but it's actually going up, then you are like way into the overfitting situation. Okay. Now with deep networks, the idea is unfortunately not the same as some of the non-deep models that you've seen before, like logistic regression, SVMs, and so on. Because with deep networks, there is some recent work which captures the idea that you could overfit like anything on the training data and still have good generalization. Okay, so it's a different phenomena with some partial explanations, which is not in scope for us. This script is focusing on the more traditional explanation of validation versus training differences. Okay, so what I'm trying to say is that there is some evidence and some line of work which has shown that you could over parameterize and get to 0 error and still do good generalization. Okay, which is a different regime altogether. So anyway, this does provide some picture, but it's not like a complete. Yeah.
So just scroll down to that map.
Mm-hmm.
So over here you have the tiny data, that is the smallest model.
Yeah.
So it has a very less number of hidden layers and very less number of parameters.
It's one hidden layer. Yeah, one hidden layer.
So we are not doing a dropout in this model. Right?
We will do dropout later. We'll get a dropout. That's why I'm showing this.
So, but it's taking too much. It's taking too much epochs to lower its validation score.
Yeah, to get to the same level, right? So I don't focus on extremes, but let's say to get to 0.6 or even 0.625, this is taking like 8 epochs versus, or whatever, 6 epochs versus 100 and something epochs, right? So there's a difference. Yeah.
And then we are dropping out some parameters in order.
Now we'll talk about dropout story later. This is just, this is just saying this is like explicitly saying, okay, I have a small model. If I have increased the model size, what's happening? At some point, I'm overfitting. I'm overfitting because it's going, validation curve is going up. There's no dropout story yet. I mean, there's no regularization story yet. Now we're going to say, oh, we know that we're overfitting. Let's now start adding some regularization. It could be L2, L1 regularization that you've seen before. And we'll do that actually later.
Conclusion is, your smaller the model, the better it will generalize for the data.
No, it could be underfitting also. We are only talking about the overfitting story here, right? I mean, for this example, we are focusing on the overfitting story, but we could be massively underfitting. Like if you use a linear model, sure, I mean, you may have some number, but you may be completely like it may have like your linear model may be like 0.8 and flat, right? It could also happen. Yeah. So anyway, this is just showing as you increase the model complexity for the same data set, you might need less epochs, but the risk of overfitting and really overfitting, right? So then what they do in this notebook, and by the way, this is not like as I said, this is a specific data set, specific trends. Doesn't mean every data set will have these trends. Okay, so that's why I said rules of thumb or basically observations. They could be generalizable, they may not be, but it's something that they investigated for this data set because they could run so many different experiments, right? It's worth doing that if you have the bandwidth to do so. So now, in the next section, they're talking about preventing overfitting, and one of the ideas is exactly what we discussed in lecture 1, L1 and L2 regularization, which you've seen in even ridge regression and lasso regression about L1 and L2 regularization, right? So you can add that, and in fact, they add that for the large model. Let me just see if they mention that somewhere. Oh yeah, so they add L1, L2 regularization with the large model, and this is the result. So what are we showing? It's exactly the same curves. Now instead of log scale, again we went back to the linear scale, and what we did is the purple curves are the large model with L2 regularization with a specific L2, the constant in the front. Okay, so what you can see is now it's not at least circulate going up yet. Obviously, if you do more and more epochs, perhaps you could probably go up in the validation curve. So validation is stabilized, and training loss is going down. So which is again still you're kind of hitting the boundaries of overfitting here. But you can see that this performance is kind of matched by almost so many more epochs for the training data. So you are able to, by just doing L2 regularization, you are actually able to restrict the capacity of your model quite a bit so that you're away from overfitting reasonably okay for now. I mean, depending on number of epochs. Okay. So similarly, you can do dropout. Okay, dropout is also an effective heuristic. I think there's some discussion about it, what dropout means. But again, we can do dropout for the L2 model. Let's say the large model. Okay, so what is dropout? It's actually, you can see here how dropout is done. So this is the description. So TensorFlow is a little bit different from PyTorch, so hopefully it's not too jarring. But you have defined dense layers, which are just linear layers. And then you're saying layer to dropout, layer to dropout, layer to dropout. Okay, this is something you've seen probably in assignment 1. So this is how you call dropout, and very similar format in Torch as well, PyTorch as well. Okay, so this is how you're adding dropout regularization. Okay, so and they're doing some different type of activation called LU instead of ReLU. So, but those are all details we'll skip. So here's the dropout one. It's not that good, but you can see, for example, the brown curve, the dark curve, training is the training loss, and so you are actually hitting 0.5. You are kind of overfitting because the validation loss is actually hockey stick, right? It is going back up, so you are actually kind of an indication that you're overfitting. So if you had trained more and more and more, it would probably kind of go up and up. This will diverge. Okay. So that's, but but the thing is, let's say you know that you're diverging here, maybe you stop at this epoch, and whatever model you have, these are reasonably comparable to the, or probably better than the ones from the tiny model. Okay. And finally, so what they're saying is it's actually not that good. So it's both these regularization approaches improve the behavior of a large model, but this still doesn't beat the tiny baseline model, in the sense that you can see that you can look at the horizontal lines and see that, okay, they're kind of similar. Obviously, you are gaining in terms of number of epochs, but they don't really beat the tiny model or anything. Okay. And the large model has way too many parameters. So then the last thing they do is combine L2 and Dropout. And then they have this curve where you have to focus on the pink lines only. Okay. So just ignore the purple and the brown. And here you can see that at least, you know, the order is kind of reversed, like the training has higher transitivity loss than the validation, but at least they are actually now way better. I don't know, not way better, but like you can see that, you know, there's a few percentage like points improvement compared to the tiny model. So if you kind of extrapolate, it's closer to the 0.5, 0.55 something, whereas the tiny model is still above it. And tiny model will take a long time. I mean, it's not like if there's a gap of this much units, tiny model might take another 2,500 to kind of close that gap. So so that's the exploration that they did with this particular data set to get a sense of controlling overfitting. The underfitting story is not there in this notebook. Okay. The underfitting story is just exactly what we saw in Playground, right? So if in Playground or TensorFlow.org, if you use a simpler model, you can't really get the decision boundary. So you have to kind of increase the complexity so, you know, little bit, so that you actually get the decision boundaries that you care about, especially when the data is not separable. Right. Any questions here? Okay, if not, I will switch to the new slide deck. So we'll just get started with this. You know, it's good in one sense with that it'll be as if we were covering the full slide deck next time, but it's good to get started. Before that, I did want to, before we switch to text, okay, so the next slide deck is all about text and embedding, text embeddings and so on. I wanted to show you again a 7-year-old paper. It's called Densely Connected Convolutional Networks. Okay, so these are all, I'm trying to show that these are all somewhat recent. Sure, 7 years is a long time, but it's also not that long of time in these things. And so this is like the best paper in the top conference in computer vision, which basically images, videos, and so on. And that paper is basically trying to make stick connections between tensors. Okay, which means what I mean by that, this paper is just, the idea is you have a tensor, instead of just passing to the next layer, pass it to the 2 layers later, 3 layers later, 4 layers later, and every layer is just passing the tensor not just to the next layer, but also 2 layers later, 3 layers later, and so on. Okay, so obviously to do that, you need to ensure that the tensor dimensions are kind of appropriately sized so that you can actually pass them forward and they can be processed, right? So for example, this layer is this layer is processing both the green curve and the red curve. This one is passing both the purple curve, green curve, and red curve, and so on. So there's some extra work that needed to ensure that happens. But using that, they show that so they've added extra connections, and they show that they improve on CIFAR 10, which is what you will use in your assignment. They show improvement on CIFAR 100, which is a 100 class classification, a bigger data set, and some other street numbering and ImageNet data sets and so on. Okay, so just to show you that what is possible with some simple ideas. Okay, so anyway, that was just a blurb about CNN, since we were talking about images. So now let's talk. What we're going to do is not really cover the entire slide deck, but really just introduce NLP, at least introduce NLP problems at the minimum, and maybe just do Naive-based recap, because that's something we've seen probably before. So intro to NLP is going to be very, very broad and very, very, I would say, informal. But let's see how it goes. So natural language processing is the concerns with all aspects of natural languages, which is our communication languages. not computer languages, basically. So, and within that, we only sample a very narrow set of problems and concerns or concepts. Okay. And in particular, what we care about is how to deal with text. Okay, text is a bunch of symbols, and those symbols are not numbers. And we know how to deal with numbers because we can put them in vector spaces, and we can do additions, multiplications, subtractions, whatnot. But these symbols, we don't know. We don't have a a way to manipulate them directly, right? So obviously, there are several ways to kind of work with it, even if you did not know any new advances of NLP, which is you can just do one-hot encoding. So you can just literally say, hey, indicator of word being cat, indicator of word being dog. You can just have a vector where some location indicates that the word is something. That's just the one-hot encoding, and you would have seen that perhaps before. And there are also other transformations that you can do based on frequencies and so on, DF, IDF, and so on. But we'll see some other methods, maybe not today, but next time. But let's first talk about a couple of use cases. And these are very classical, so you might have seen it before, you might have used it before, but just to kind of recap. The first one is machine translation. That's the technical name people use for this task. I mean, one of the popular examples is through Google Translate, but basically machine translation involves going from one source language to one target language. Okay, so you want to translate, hopefully grammatically correct, going from one language to the other. And it's a fairly non-trivial task. I mean, it's kind of easy today with really large powered networks. But even a few years ago, it was pretty hard to do it. You can't just do translation. You can't just map the word to the destination language word by word, because that would be a very bad translation. The next example is query answering. So here's an example of a problem where it kind of is a very elementary way of doing the type of things that we can do with LLMs today, large language models today. So where you have a document and you have a question, and there's an answer in that document that you want to kind of isolate out. Okay. So for example, in this document, there's some description, and then who does the article say will not press charges against somebody, and who that person is needs to be identified. And generally, this type of data. So this is the application. You could always collect data with this triplex, right? You can say document, query, and then in the document you can identify which is the string, which is the answer for that, and hope that with that triplet you can learn, the mapping from a document query to an answer. Okay, you could do that. So it's going to be like some sort of classification problem. So let's worry about solutions later. So the next one is speech to speech. It's not exactly language, but typically you do go through a language language layer. So you could you could potentially envision a situation where you could just do you can just go from speech signal to speech signal of two different languages. But here we're showing the route from speech to text is through automatic speech recognition. And then machine translation, which we just saw 2 slides ago. And then once you have the text to speech, TTS, these are just acronyms that you will see again and again, maybe in the literature and elsewhere, to go from text to speech. Okay. Now today you can actually get, for example, OpenAI, the vendor, provides not just large language models, but also provides pre-trained models for doing text to speech and automatic speech recognition, right? So not just OpenAI, actually, if you go to Google and Azure and Amazon, and not just them, but there are actually many other companies which provide either something to do with this part or something to do with this part, or maybe all of them. Okay, there are many companies which allow you to use pre-trained models as is, and they also allow you to do fine-tuning, which is exactly the thing that you saw for images that you will see in assignment 2 as well. Okay. And another example is visual question answering, which is now introducing multiple modalities. The question is in English, but the input is in is not it's not a sentence or it's not a document. It's actually an image. And so this is called multimodal. So where you have multiple, it's not multimodal in the statistical sense. That's also like having 2 modes and stuff. But here it's just 2 different types of data sets. Okay, 2 different data sources. So you can ask English questions, and then your training data, this visual question and answering, is a use case where the training data will have image, questions, and answer pairs, and then you would somehow map it to a supervised learning problem and actually train on that, and then therefore it will be able to answer, set up a VQA system for you. Yeah, and today you have multimodal LLMs also, which can answer, like you can upload an image and say, ask these sets of questions. Okay. Here, I'm just pointing out a couple of issues with natural language. Is the thing about ambiguity. Okay, not just ambiguity, but also colloquialism, or basically we can interpret things which just based on our culture and so on, which is probably not easy for the computer to learn. But maybe it's not so, it's not so severe today with LLMs. First one is sense, right? So I saw her duck, right? Doesn't mean I saw somebody owning a duck, whose duck I saw, or did I see the person ducking down a table, right? Going underneath the table, right? So that sense is not going to be clear from just these 4 words. It's going to be clear from a larger context. Okay. Similarly, idioms are kind of, he kicked the goal, he kicked the ball, he kicked the bucket. He kicked the bucket could mean something different, right? Somebody passed away is also considered, it can also be, you can use this sentence to refer to that. And so again, these 4 words will not be able to kind of tell you what the context is. Okay. And even maybe the larger context may not tell you what that means. You may just need to know from generally the English language that, okay, there are these things called idioms, and this is one of the idioms. So that's what it means. Okay. Finally, reference is also a big issue, where the ball did not fit the box because it was too big or small. The question is, what does it refer to? If you say it was too big, then it might refer to ball. If it was too small, then it might refer to the box. So there is a reference aspect which is non-trivial for for machines to pick up. Okay. So they're just trying to show some complexities in NLP processing. But we'll not look at there are models that can handle at least some of these simpler issues today, like GPT-4, for example, can handle many of these things that I'm showing in the previous slide. But it's good to know that these are the challenges which were kind of conquered from basics, right? So what are the basics? So we'll look at a couple of models here in this section, and in fact for today maybe we'll look at maybe 1 or 2 models. Let's see. Okay, so let's start with some basic models. Okay, these models don't really do anything with the text. Okay, in the sense, nothing intelligent with the text, maybe just one-hot encoding or just counting or something like that. Okay, so the first one, in particular, let me just say what these models don't do. And what they don't do is they don't relate words with other words. Okay, there's no way to say a cat and a dog maybe is words, they're like closer to each other than a cat and like a house, or a cat and an airplane. Like they maybe not, like they're not even maybe appearing in the same context. Okay, maybe a cat and a dog can appear in the same context. Okay, so that's what I mean by word-word relationships are not kind of front and center of these models. So I've listed a bunch of models, but we'll actually look at maybe 1 or 2. Maybe let's look at 2, because I've been mentioning large language models. Let's at least say what is a language model today, and then let's also look at Naive model. Okay, this is just a recap. Naive is a recap of a previous model, and maybe you've also seen a Markov language model, so we'll also see that one as well. And the remaining stuff we'll see next time. Okay, so how many of you have seen Naive before? So everybody has seen Naive model before. Okay, then it should be definitely a recap. So let's see how it goes. So Naive is a generative model. So I know there's a lot of emphasis on generative AI to generate new things, and we'll see that idea a few slides later. But so there's this notion of discriminative models versus generative models in machine learning, and it was before, even before generative AI term was coined. And generative models just mean that we are modeling the entire distribution of both the features and the targets, rather than the conditional probability of targets given features, which is the discriminative setting. Okay, and what is the key assumption in Naive model is that if you have targets and features, in our case, with naive-Bayes, in a spam filtering setting, the features are going to be indicators of whether the word was present or not, and the target is going to be whether it's spam or not. Okay. So in naive-Bayes model, the assumption is going to be an assumption about the conditional probability of the words, conditional probability of the features given the target. Okay. The conditional probability of the features given the target is that the features are conditionally independent of each other given the target. Okay, that's the assumption. Okay. How many of you you have seen this before, and maybe this is kind of easy to explain, but this is a key assumption which underpins this model. Okay, so this is a assumption about the joint distribution between the target variable, which is spam or not spam, some sort of binary variable, and all these are also binary variables, which are just saying indicator or presence or absence of a word. Okay. So just say there's a bunch of binary variables and there's a joint distribution on them. And one of the properties of the joint distribution is that the conditional distribution has a conditional independence property. Okay. So if the conditional independence property is true, this is the assumption, then you can say what is the probability of the target given the features, which is what we care about. This is the conditional probability. This is what we care about. This is proportional to by Bayes rule, proportional to the probability of the target times the conditional probability of the features given the target. Okay. The proportion 2 is because there's a divided by the marginal probability of the features, which I'm skipping. Okay. So Bayes rule, if you remember, is basically so what is this right hand side? So the right hand side is actually the joint distribution between the target and the features. Okay. The numerator, so sorry, this right hand side. What's missing? Why is it proportional? Is because the joint distribution divided by the marginal distribution of features is exactly the conditional distribution of the target given the features. Okay, so that's just a definition. Any questions here? No questions? Okay, so this is the assumption. This is the model. This is how you would make the classification. Which means that what you need to know to do a classification for any given collection of words is to say whether it's a spam or not, is to know what is the probability of spam from data, and also to know what is the probability of each word given a target. Okay, so if you know those numbers, then you can say, oh, okay, give me a bunch of words whether they're present or not, and then I can compute this number for both the spam class and the non-spam class by just knowing these numbers. And then whichever number is the highest, that's my prediction. Okay. So what is the estimation then? So we just need to estimate the marginal probability of being in class 1 or class 2, and the conditional probability of each word occurring under each class, under each target value. Okay. So sorry. A picture before I just show the diagram again. Sorry, show the estimation aspect again. Is that so? This is a figure that comes from the literature called probabilistic graphical models. Okay, this was a very popular, and this still is a popular subfield in machine learning, which tries to capture explicitly the relationships between features and targets. Okay, so one of the advantages of this methodology, which I don't think is taught like in ML 101, perhaps I don't know, is that it can let you explicitly capture a very rich amount of domain knowledge. Okay, this domain knowledge that under the class these things are independent is an assumption you're making about these random variables. So you can imagine much more elaborate graphs, not just class versus features, but you could have much elaborate graph with lots of interpretable variables, and then you can talk about something being conditionally independent of something else, given something else. Those are all information that are very nicely captured in such graphs. Okay, that's why they're called graphical models. These graphs support something about the joint distribution between the random variables. Okay, in our case, we know that the joint distribution between the random variables, at least the conditional probability of these things is independent given the target. That's some property about the joint distribution that we know. So this picture here is kind of shown like this because you don't want to copy the same node again and again. You put a box and say how many times the feature vector is present. So this is called a graphical model, and it's just a very tip of the iceberg. There's a lot of work in terms of estimation as well as inference for these types of models. Okay, a lot of work, and there's a 500+ page book by some authors on this. If you're interested, I think it's on the, I don't know if it's on the syllabus page, but if not, you can let me know, and I can let you know about the reference. So coming back to estimation, right? So as I said, there are two classes, binary features, which is like presence or absence of a word. Then firstly, right, we just need to count the occurrences of feature for under each class, right? And then we also need to count the number of occurrences of spam versus not spam. Okay. What do you mean by that? So you just need to know the marginal probability of how many times. So if your data set has 1,000 emails and labels, then among the 1,000 emails, if there were like 100 were spam, then the probability of spam is 100 divided by 1,000. Probability of not spam is 900 divided by 1,000. So at least that parameter you know. And then under the 100 spam ones, how many times did word 1 occur? How many times did word 2 occur? How many times did word 3 occur? That's the count that's going on here, and that's it. So that's those are the estimates you get, and you can do that for under both target classes, and you can get all these parameters, and then you can just plug them in for any new collection of any new email indicator of each word. Whether it's probability of spam or not, you can just plug in those numbers and see which number is higher, right? Okay, so that's naive base. So I want to stop with like a one small model. It's easy to explain, so that's why I'm going to squeeze in the next 10 minutes. And we can probably revisit again. So this is called a Markov language model. Okay. So what is a language model, right? Language model allows you to generate new text. And we're going to talk about a character level model. It just means that we're going to generate new character at a time. Okay. So language models are just supposed to tell us, given the current set of words, what would be the likely next word. Okay, that's what they want us. That's what they model. Okay, so character level model just means what's the next character given the previous characters. Okay, so a Markov model, a Markov language model, just uses Markov statistics. Okay, well, Markov statistics just means count statistics. We just need to know in the data how many times did, for example, L appear when the previous few letters were HEL. Okay, how many times did E appear when the previous few letters were H and maybe a space bar? So it's just computing Markovian statistics and using that to generate new text or new characters here. Okay, so this problem of creating a language model using Markovian assumption can be modeled using a simple maximum likelihood estimation method. And in fact, we don't even have to use explicitly what is called this maximum likelihood estimation idea, because at the end of the day, it just boils down to counting and normalizing. Okay, what do I mean by that? So let's say we pick a Markov order of 2 or something. Then what we're doing is, for in the training, we're picking words, and all we're saying is, for every 2 previous characters, what's the likelihood of the third character being A, B, C, D, E? In this example, what's probably this character being L, given the previous 2 characters being H and E. Okay, you kind of remember those conditional probabilities. So how many are there? If there are 26 characters, then 26 times 26 would be the condition thing. And then given that, there will be 26 valued probability mass function, which will say under this each of these conditions, what's the probability that you will get an L, what's the probability you'll get an X, what's the probability you'll get an A, and so on. Okay. Once you have these numbers, you can that's the definition of the model. So you can start with, you need to start with 2 letters somehow. Let's say we start with 2 letters, and then you can always sample from these conditional probabilities to get the next letter, next letter, next letter, next letter, and so on. Okay. Any questions here? No questions? Okay. I wanna stop here, but I want to check your understanding of this simple model. It's just a way to, if you have a lot of words, just you need to figure out what's the frequency of the third character given the previous 2 characters. Okay. any character given the previous two characters, actually. So you can include space bars also if you want, or basically white spaces if you want. And that way you can generate a string of characters if you have these empirical statistics. Okay? So these statistics are actually very similar to the statistics that you saw in the naive-Bayes model. Naive-Bayes model is also just how many times did the word occur under the class, is just how many times did the word and the class occur divided by the number of times the class occurred, right? So yeah.
This model is probably being used in smartphone keyboards, right? When we just type 1 or 2 letters and it predicts which one we are most
Yeah.
likely to.
Yeah.
Type.
Yeah, you can use this solution for that. Yeah, I don't know if the current keyboards are using this, but yeah, this solution is a good candidate for that because it's very simple to estimate counting and normalizing. In fact, it can be adapted to anybody's specific way of typing also. So yeah, this is a good example. Auto completion is a good example here, but you can use other models also, and we'll see a lot of much more advanced models next lecture and so on. Okay, if there are no questions, then this is where we'll stop. Yeah, we'll continue next time, and the assignment 2 is due before the next lecture. Yeah.